In a follow-on paper, Alfvén explores how interstellar clouds could lead to the formation of stars on a chain, and how each could lead to the formation of its own planetary system. This work builds on the previous work he had produced on the formation of the solar system. Let's find out more about his ideas. Understanding how stars form has always been a key concern of astrophysics. There is a general agreement that they have formed out of interstellar clouds, but not a real consensus on how this process actually occurs. There is convincing evidence to suggest that these clouds are actually ionized, and in the past magnetic fields have been thought to hamper the formation process. It is time that the plasma physics was used to truly understand this process. So in order to understand this, we have to look at some general properties of cosmic plasma. So firstly, cosmic plasma must be considered to be non-homogeneous, having a filamentary structure produced by electric currents. Secondly, when currents flow parallel to the magnetic field lines, plasmas have a tendency to set up electrostatic double layers, and the concept of frozen-in magnetic fields is therefore redundant. Energy transfer can take place at double layers. From a source of energy such as the kinetic movement of plasma, energy can be transferred to a distant region where it is released in particle acceleration or noise generation. In plasma there are both ionized and non-ionized atoms, and when the velocity of the non-ionized atoms in relation to the ionized ones exceeds a critical velocity, rapid ionization of the non-ionized atoms will occur. The same will occur when a grain moving through this magnetized plasma produces a large transfer of momentum and a significant heating effect. Turbulence of fluids is generally described when the velocity of the medium is truly random. It is often claimed that the turbulence is an important phenomenon in cosmic plasmas. Measurements from the magnetosphere tend to refute this claim, instead pointing to a highly structured plasma where velocities can show rapid variations due to the filamentation rather than the random turbulence. By contrast, the atmosphere up to the turbopores is often in a state of turbulence, and the ionosphere, however, shows rapid variations in the lower part due to the convection produced by local heating. In the upper ionosphere, these are mostly due to the current patterns. Turbulence is often associated with mixing, and this is not what happens in a plasma filament. It is quite the opposite. Magnetic fields give structure to the low-density plasma, which suppresses or even prevents turbulence. Turbulence therefore plays no major role in cosmical plasma. Far from mixing plasmas, they have a tendency to separate. There are many complex reasons this happens, and one reason is due to the different laws of motion of ionized and non-ionized components of the magnetized plasma. The condensation of non-volatile substances to grains constitutes another, and all the variations in the separation leads to large variations in the chemical composition of planets and satellites, and possibly stars too. Now, it was believed that the main way plasmas were ionized was through ultraviolet light, and we now know that this is not true. The majority of plasma is ionized due to the hydromagnetic transfer of kinetic energy or gravitational energy into electric currents, which ionize. It therefore follows that a star forming from a dark cloud represents the release of gravitational energy of the order of several thousand times the sum of the ionization energies of all the atoms in the whole mass. Therefore, any collapsing gas cloud would rapidly become ionized. Dust can be expected to play an important role in interstellar plasmas. The interaction between these dust particles and the plasma will play an important role in understanding the dynamics of such things as stellar formation. Solid bodies in space, such as these dust grains, are usually electrically charged in relation to the surrounding plasma. And there are two competing effects: the photoelectric effect, which will give solid bodies a positive charge around a few volts, and the ambipolar diffusion, which will give a negative charge, and the charge is related to the electron temperature, but again is normally around a few volts. Now, if the grains become charged, electromagnetic forces will dominate its motions, and in some senses it can be considered part of the plasma. If the dust cloud is large enough, the majority of the free electrons in the plasma may be absorbed by the dust. In extreme cases, it may therefore be possible for plasmas to consist of heavy negative dust particles and smaller positive ions. Now, dust usually consists of particles of a variety of sizes. The large sized particles will have an almost negligible charge compared to the smaller ones, so their motion will not be dominated by the electrostatic, instead they will be dominated by gravitational forces. Now, particles which have an intermediary size might see their charge change rapidly, changing their behaviour from gravitationally based to electrostatically based. And this makes understanding how plasmas behave out in interstellar space so difficult. There are so many factors that affect its behaviour. Only recently, scientists have begun experimenting with dusty plasma aboard the International Space Station and discovered many strange behaviours. So let's look at the hydrodynamics of a cosmic plasma cloud. The electromagnetic forces are decisive in the formation of cosmic clouds and keeping them together, and there are three special cases that we must consider. So number one, the current flows only in the toroidal path around the magnetic field, and this will lead to an electromagnetic force which is directed radially outward. Number two, a force-free configuration where the current and the magnetic field run in parallel. And thirdly, an axial current and a toroidal magnetic field will create a Z-pinch. And even if the gas pressure is zero outside of a certain radius, the plasma can be confined inside the radius of the current if it is sufficiently large. Now, if the magnetic field is force-free, it neither adds nor counteracts the contraction, and in order for this to happen, the current must flow in the same direction as the magnetic field, and in the case of cylindrical geometry, this will create a spiral pattern. If we change the angle between the current and the magnetic field lines so that the current becomes more toroidal than the magnetic field, the electromagnetic pressure acts in the outward radial direction so as to counteract a contraction. If on the other hand the current becomes more axial than the magnetic field, the electromagnetic force tends to pinch the plasma together. Now, the main factors that will affect an inward contraction is whether the magnetic field is more toroidal than the electric current. And in the magnetosphere, we see both parallel and perpendicular current systems. The auroral current system consists of magnetic field aligned currents, Birkeland currents, which close through currents perpendicular to the magnetic field. So in the ionosphere and the equatorial plane, they are perpendicular to the magnetic field and parallel in the highest parts of the ionosphere and most of the magnetosphere. So how would we go about star formation in a dusty plasma cloud? So according to the conventional view, star formation is due to Jeans collapse of a massive interstellar cloud, and effectively that just means under the act of gravity. The problem is that clouds which are smaller than about 100 to 10,000 solar masses will not lead to a normal collapse, and they've had to invent a complex mechanism to support that collapsing process. And the problem is this does not even lead to the formation of planets around stars without additional ad hoc assumptions. So Alfvén suggests an alternative approach which could be based on the three following assumptions. Number one, cosmic plasma physics, based on concrete proven laboratory and observed effects, should be used. Number 2, interstellar clouds are not necessarily contracted and kept together by gravity. Magnetic fields similar to the ones in the magnetosphere and the heliosphere are likely to exist in interstellar space, and these will act to collect the gas and compress it, and this implies that the gas clouds of any size can be formed, even if the gravitational strength will be too low to pull them together. The current required to produce these effects are not excessive. Number 3, even if the gas is not held together by gravity, a dusty cloud is inherently gravitationally unstable, in the sense that the dust will tend to move towards the centre of mass. And once a dusty ball forms, it will cause more dust to be attracted via gravitation. And once it is large enough, it will be able to attract neutral gas towards it. Now, we have discussed how cylinders of gas can carry currents, and in certain situations this can cause a compressive force to arise directed towards the axis. And if we were to extrapolate to a larger scale, it becomes obvious that an infinitely long cylinder would be highly unstable, and what is more likely to occur is that the cylinder is broken up into a series of smaller clouds, in each of which one or several stars may be formed. And what is interesting is this is exactly what we have seen in some of the images from NASA recently. We see stars forming on long chains. Now this is exactly what Alfvén predicted in 1977. Alfvén goes on to discuss the equations for the motion of the dust in the plasma based on their size, and I will not cover the details here, but as always, if you're interested, I will link the paper down below. So how does sedimentation of dust work in a gravitational field? So even if the dusty plasma is kept together by the electromagnetic forces, the gravitational field may play an important role in the motion of the grains and the larger bodies. Alfvén goes on to show that this simple force of gravity can pull together a spherical dust ball in a given period of time, and he calculates that for a cloud of a particular size, there is an equation which will determine how long it takes for the particles to fall together under that force of gravity. Now, interestingly enough, he actually shows that it is very much dependent on the size of the particle. So if we were to take a cloud which was of the same size as our solar system, so about 5 billion kilometers, then this would be expected to form a dust ball of approximately half a kilometer in size, depending on the size of the particle. So if the particles are really small, it will take a considerably longer time for it to form. So if we take a particle of size 0.1 micrometers in radius, then this will take approximately 1 billion years to sediment to the size of about half a kilometer ball of dust. If, however, we increase the size of the dust particles to about 0.1 centimeters, this now only takes 10,000 years to sediment into a dust ball half a kilometer large at the center of this cloud. Through observations, we know that small particles, meteoroids and micrometeoroids, obey a size distribution, which means that as the radius increases, so does their rarity. The mass distribution follows the opposite law, showing that larger particles represent a larger integrated mass than the smaller ones. Now, very little is known about the size distribution of dust particles in interstellar clouds, so a reasonable assumption is that they will follow a similar distribution as the particles in interplanetary space, meaning that the majority of the total mass could be stored in larger particles. And as the accretion time depends linearly on the size of the grains, the time of accretion may be set essentially by the formation of large grains in the dusty plasma. And the process of grain formation in dusty plasma at the moment is still poorly understood. The turbulence, as we've already discussed, plays no part in prohibiting the sedimentation process. The irregular motions observed are likely due to propagation waves, and these will not inhibit sedimentation. The nucleus of the dust ball may be formed by very large grains in a rather short time period. So how do we form the protostar out of this? Now Alfvén goes on to work out that if we took a ball of dust of mass md with a radius of rd, then he calculates that it would have an escape velocity of v. And around the ball, an atmosphere with a maximum density of Nm is formed out of the surrounding cloud, which has a density of No. Now once the dust ball has grown large enough, so to about the size of the moon, assuming a gas temperature of around 100 Kelvin, a runaway process of accretion will take place, leading to the steady decrease in the density of the surrounding cloud. Now, for a cloud of solar mass, the critical size of this dust ball is reached when its mass is about 1/1,000,000th the size of the original cloud. And this he then refers to as a stellissimo. Now, a non-rotating, non-magnetized cloud will quickly become completely accreted by the central body. Magnetization and rotation puts an outer limit to the region of accretion, and the result is an almost void region around the body, surrounded at a large distance by a partially ionized dusty plasma cloud, from which the neutral particles and gas will fall in towards the central body. Now this infalling material will become ionized when they reach the critical velocity and results in the formation of planets. Now if the cloud is non-homogeneous and consists of a number of smaller clouds, it will result in the formation of several stellissimals of various sizes. Now the largest of these may end up attracting and capturing some of the smaller ones, leading to the formation of binary and multiple star systems. These intermediary stellissimals may be between 1,000th and 1,000,000th the mass of our own Sun. The process of star formation discussed would lead to the condensation of most of the cloud material which originally was located inside a certain limit. Now outside there exists a dusty plasma hung up on the initial magnetic field, and the neutral material may then fall in towards the central body, allowing for the formation of planets. Therefore, the properties of the planetary system are determined by the mass and the spin of the primeval star. No planets could form until the stellissimal accretion process had completed, similar to what we discussed in terms of the formation of the satellites around planets cannot form until the planet is formed. Now, the surprisingly high regularity of the main asteroid belt in our own solar system shows that since its formation, there cannot have been any high eccentricity celestial body large enough to disrupt it. So what are the main conclusions from this model? So he draws 4 conclusions. The first is the magnetic field in interstellar gas clouds can aid the compression of gas, and it is highly likely that these dark clouds are kept together by electromagnetic effects, not gravity. Number 2, in a dusty cloud, gravity collects the dust at the center of mass of the cloud, and a dust ball is formed which, when it has grown large enough, is able to collect the mass from the surrounding cloud, and this process will lead to the formation of the star. Number 3, in a cloud of irregular structure, a number of these dust balls may form, and these may end up being captured by the largest dust ball, leading to binary and multiple star systems with similar sized stars with similar angular momentum. And number 4, this process accounts for the collapse of smaller clouds which the conventional model cannot. So is this the Holy Grail? Well, probably not, because our understanding of plasma has significantly moved on, and our understanding of how Birkeland currents form across space has also moved on. But there are a lot of key points, similar to when we looked at the solar system, that I think we need to take away from this, and that is that gravity will still play a role in that accretion process, in the formation process. We can't simply ignore it, because there will be neutral material in these clouds, and gravity will act on it. I'm not sure at the time that Alfvén, when he wrote this paper, was aware of the fully electrical nature of our sun. I think this idea is still based on forming enough matter to start that nuclear process. So there probably is a nuance between where Alfvén is and where the reality lies. But I think it's important for us to understand from those early pioneers what their thinking was, and then be able to compare it to the more update model to see the differences, rather than just looking at the new model and going, yeah, but why is that? You know, if we can understand where this process has come from, I think it'll help us to understand and to see the pattern of how all of these different things fit together. I don't think there is a golden arrow, silver arrow, that will fix everything. I don't think there is one model that explains everything at the moment, and it is finding those different ideas which make sense, and then if something else comes along that is better, fine, then we replace that. So hopefully that is food for thought. As always, be brave, be curious. The truth is waiting for us. Until next time.